Hi everyone, so we still have got Venkat here with us. He's now moving on to his presentation on URDF using ROS2. So he's gonna give us a presentation on a live robot about his project and what he has done. And after this, he will be evaluated and he would stand a good opportunity to win a certificate from us. So we're gonna have him share his screen and then he'll start presenting his project.
Hello, can you hear me?
Yes, I can hear you. Let me just get your screen showing. Okay, now we can see your screen. You can go ahead.
Okay, so hello, my name is Venkat. We are trying to get into the details of URDF, which is Universal Robot Definition Format, wherein we actually define a robot and we try to get all the respective sensor related information into the simulator. So let me show you a quick demo and then we will get back into details with that. So we can see my screen well.
Yes, we can see your screen.
Okay, so here is a real robot. I'm connected with this robot, and it is actually streaming information about its position and other information. So as you can see, you have various information over here. This is about the robot model, the transformation information, images and cameras today. I think we are having a glitch there, but we'll have an odometry information to show you the position of the last information. I'll try to move this robot and live, and we will see that it actually moves along with that on this. So I'm going to use the same program we have, which is basically for. So here is the real robot. Here is my screen, which is going to do the movement, and I'm going to need the visualization tools, which are graphic tools, which is ROS2 here. So I'm going to highlight this to actually see it. So as you can see, I'll try to move the robot. Okay. So as you can see in the demonstration on the right side, so you see that the RVs, it actually is moving along with the information related to position information. It is having the laser scan data of its surroundings. So as I move around, so you can see that it is actually adjusting its laser. Let's see that. Okay, there you go. So I can continue to do this. Okay, as you can see. Okay, there you go. All right. So this is publishing. So the this robot and I think towards the end of this presentation, we'll try to understand how does this robot information and this RVs come together, and how is this how is the RV simulator over here made to look like as close as possible to the turtle bot. So that is going to be the focus of this presentation. Okay, so as you can see, it is nearly the same. I mean, I can't say I can't say it's the same at all, but it was made to look alike a little bit, so that it actually represents most of the robot's physical properties.
Okay.
Okay, so let me go into the presentation. So do you want to see something here? I might lose the robot when I come back. So I think it is we can the pose estimates with the next one with nav. But as you can see, this is reading information from the ODOM. Okay, so the ODOM related topic, that is the odometry information. There's the transformation information. The robot model has multiple links. We'll get into the details of how these links came to be,
Okay.
and what these different links actually came, how they come together, and how the structure is formed. These are all the links that you actually see over here, and the links and the joints, and a little bit of basics of URDF. Okay. Can I move on to the presentation? Is that good? Seeing the real robot?
Yes. Let's go on.
Okay. Okay. So let's go back to the. Sorry. Let's go back to the presentation. In the presentation, so let's see multiple properties of this, so you can see it well. So we started with this. It was a very detailed specification that was provided to actually make this work. As you can see, this is a view. I think what I started doing was that I started taking this and started calculating what is the distance of different links from each other and started constructing it. The weights information was used for calculating inertia and other properties, which we will discuss. And weight unit and dimensions were used to calculate inertia and others. There are different parts that are actually used, which are closely resembling but not fully functional, obviously, as the real robot itself. This is the closest Turtlebot 3. It's a pro model. That's what it looks like. We'll try to get as close. I try to get as close as this. But let's first talk about some basics, so that I give the audience a little bit of context. So what you're seeing on the right side is called the end effector. So it's like let's say there is if you can see this clearly, this any part that actually is a single unit, it's called a link. That's called a link that gives these are rigid bodies that actually give the structure to the robot. And between two links, you use a joint. There are different kinds of joints. We can call them as the movable parts. Usually, that will be a combination of a gear, a motor, and a encoder. Okay. And if you these are different, there are different kinds of joints, and a group of these joints and links can make a kinematic chain. Okay. For example, your entire arm is a kinematic chain. Okay. And then there is degrees of freedom. Basically, when these joints move in combination or differently, they create a freedom in the volume space. So if you can see that this is the end effector, which is the, let's say, the hand of the robotic arm, that will actually as you keep moving this is the entire workspace of that arm, right? So it has the degrees of freedom is how many degrees, how many angles and how many positions you can actually take to create this workspace volume to reach this. This is called the putting together all the places it can reach. It's called workspace. Okay, so this is just some very basic things for you so that you understand where joints come from. So, speaking more of joints, so let's take a joint. Right? The joint has, let's say, in the calculation of transformation matrices, you will actually have frames that are associated so that you can start with the base frame and then move to the understand the end effector's position. And let's talk about three different kinds. One is a revolute joint, which means that let's say you have a joint here, and if this arm can actually move only 15 degrees up and down, so that we specify that as a revolute joint where you actually have limits of its movement in a specific axis. Okay? All right. But it can rotate. A prismatic joint is more or less like a sliding joint along a specific axis. So it just goes this way or this way. It's a prismatic joint. Right, and a continuous joint is more or less like a wheel.
All right. So the reason why you're speaking about joint is you're trying to give us context about why you.
Correct. Context of how I joined a wheel together.
Okay. All right. And
because I'm going to use when I show the URDF, you will see properties of joints.
Okay. All right.
Because these properties of joints actually come back to these basics. Okay. These are continuous joints. So a wheel is a continuous joint.
Okay. All right.
And inside this, there are some sensors and they have some properties. For example, there's an IMU sensor. It actually measures the angular rate of movement. Okay, it is used for, like, we can call them as the general function is an accelerometer, a gyroscope. It's used for navigation related measurement, orientation, velocity, and acceleration. Odometer is used for measurement of vehicle, measurement of distance. This is the chip that will be there on the device. This is mostly related to the right next to the motor, where it actually has it publishes the distance traveled. Then leader is obviously our laser scanner.
Okay.
So these things exist inside the URDF file. I gave us a little bit of brief so that when I show you the file, you have some context. Okay.
All right.
And we have seen the real robot. I would like to quickly show what it looks like. My robot session has ended. Okay, gladly we saw all that. Then let me show you the real hardware. Right. So I have let's take that. If I take a view frame joint, it actually looks like for the real robot. Right. The real robot actually, you can see it well now. Please let me know.
Yeah, that's so. Right.
The real robot has a hierarchy like this, which is an odom, base front, etc., etc. So our goal is to actually try to get to a scanner. So it only publishes some part of this. From our information, is the real robot. This simulator inside the tree, actually, if I made a simulator inside the tree, it contains all the parts. It looks like this. Let me quickly zoom in to show you some relevant parts, right? So the way I constructed it, I mean, there are a couple of different ways to construct this. I started with the base skeleton of the original robot for so that the TF tree can be merged later. So with ODOM and base footprint, and then when you and then I started combining the chassis. So the way I have split this is something like this. There are a little bit more ways to do this. So if I come here, so this is chassis. Let's say that this whole plate is a chassis, right? So this is a chassis. Chassis 1, chassis 2, chassis 3, and chassis 4. And between them, there are 35 and 45 spacers. Okay, these are spacers. These go on either side. Between in the middle, there are in each link to each board is there are some items that are kept on the board. Right? So in the URDF language, what I did was I first placed the chassis, and on top of the chassis, I placed the drive motor, the batteries, and then I connected the batteries to here. So this structure of how I constructed can be visualized using this map. So let's take the first one. Right inside this, I connected the chassis, which is the bottom one, and connected to the bottom chassis is the drive wheel support. These are the back wheels. These are the side wheels, and in the front there is a wheel that is actually rotating in 3 different dimensions. The way we combine that is we have a yaw link, the roll link, and pitch link, and put them in the same place and connected one after another. Okay? And these are all linked to the chassis. Now you can see that chassis 1 is again linked to chassis is linked to chassis 1, chassis 1 linked to chassis 2, and whatever is there inside that specific linked to that specific chassis is actually connected to that chassis inside. So just to put a picture to that statement. So here, if there is a board here, this board was connected to this chassis, and this chassis is connected to this chassis. So I connected a tree like that. And when we actually merge it with the real robot, that merged tree actually looks like this. So the merged tree will have the same properties, but it will isolate the real robot's properties and this one. So we actually don't take the something like drive wheels and all. So we move the, so for example, last time you've seen the chassis had a drive wheel, we removed that for the merged tree. So when I run it on the real robot, I conditionally removed the drive wheels and I connected, and since this, when the structure got merged, the base footprint actually got connected directly here to the base link of the robot. And if you can see the rest of the physical structure that is left intact, it has no impact on the rest of the real robot case that will actually run it. Okay, so let me quickly get into the structure if it's okay. I would like to quickly show you how this workspace is organized. Is that okay?
Let's go for it.
Actually, let me show you a simulator version of what I have shown before, so that it is like so that we have something to talk about. Should launch just right now. There are a little too many commands, so I bundle them into a file. Let's see what it looks like in the simulator. It should launch 3 things: an RVs, a simulator gazebo instance, and it should actually launch the launch version. So if you see the green ones, it means that the gazebo plugins have loaded, and it is able to broadcast it properly. And if I were to see, usually this has a starting problem. We need to do this again. Not again.
All right.
So there is the gazebo instance, and there is the graphical tools that will start now, which is always.
Okay.
Okay. And there is the there should be one more. Yeah, there is all the plugins have loaded from the gazebo level because we are not connected to the real robot.
Okay.
This is what it looks like simulator. So basically what you are seeing, hope you can see it well. So there is a camera, so it's thankfully working here. There is a camera, there is a laser scan. So what you're seeing is the laser scan. We can adjust the position of this, etc. I mean the size, the point size, etc. The transformations that we saw is basically if you, I would like to quickly show you one aspect of it. Right?
Okay.
So if I go a little bit into this, so you will see that the mesh, since this is in ROS2, inside, if I show you inside Gazebo, it will show as a similar but not the same version. Just let me quickly show you from a different angle so that you can get a feel of it. I was given a mesh which is loaded only for the LIDAR for a visual presentation, visual appearance of it. This mesh is, I've used it along with this. So this, you can see it, this mesh and colors. No, I've used it along with this over here. So you can see it. I put a gazebo color on it.
Okay.
This is inside the simulator and nearly the same, but I shouldn't say exactly the same. Slightly different with material colors. The Okay, there you go. And these are the two same exact. These are the same construct, except for I have some gazebo colors over here.
Okay.
And this is just loading a normal mesh.
Okay.
I can move this robot in the same way. Let me quickly show you a movement so that you can actually. Okay, again, this needs to be highlighted. I will bind this into the bottom. There is the Brazil simulator. Is always there is my. Okay, I can see it. I can do this blindly.
All right.
It's moving together, and it actually goes back and forth. The laser scans exist. You can see this.
Okay.
Okay, so this is a stop this and if you want to go over. Okay, I would like to quickly show the structure of the your exact row files just to my presentation here.
And also, would like to see how you did the description files and the use of URDF and chakra files as well.
Oh yeah, I'm about to show you that. Yeah, here you go. That's it. I'm showing you, getting you. When I show the structure, I'll talk about them together. Okay. So let me come from the beginning of the let me come from the launch related files. Okay, so that I actually show you what it looks like. Okay. Sorry, I'm experimenting a lot. So here is a Zacro file that I actually did for the simulator. So whatever I just launched, right? So there is a visual aspect that we spawned a robot into Gazebo. Okay. We loaded the visual control complete file. We'll talk about it, and then there is a launch control file. I'll show you what each file actually contains inside this. So the visual launch control file actually contains a. It can contain. Finally, when I move to Zacro, I left URDF behind, but we can use URDF files here as well because the Zacro files eventually I converted them to URDF anyway, so I can just anytime move this. So what this file does is it actually reads the Zacro file, which is a definition of the robot, and it converts it into URDF language, and then it publishes it sends it along with the publisher. Okay? And we give inside this file, since we are doing this for the simulation, we also have a simulation file. So when the RBage loaded, it immediately loaded itself one file, which is this file that I have saved by adding all the elements manually for about all the sensors you have seen. And I saved that file. I give the same file and tell RBage to actually load this file when it actually automatically starts the script. This is the visual aspect of it. If I go back to where we actually started this, so there was a visualize, and then I spawned the robot, which is the robot description. Robot description in the robot description area. So among other things, where we add the Gazebo related model paths and plugins information, we actually do want critical thing, which is inside the gazebo simulator, we position the robot in a specific place. We can give that using this spawning of the robot. So we can set many properties in that we set a position and an orientation if we want it to. And we also give various paths over here, which is basically we need to tell where the model files are, where the environment where the plugins are, etc. The third file inside this is the launch control leader file, which is this file. The main purpose of this is that it actually spawns three things. One is the joint state broadcaster, which actually when there are moving parts, it keeps broadcasting the joint state. There is a trajectory, and then there is a uh, velocity controller. There are three controllers we actually spawn to the three plugins that you saw actually are loaded. This is required for the movement and keeping track of the where the robot is. And a control node, obviously, to actually do the rest of it. And we give the Zacro file saying that here is your Zacro file, and then you launch and control the leader. So as long as this particular item is loaded, it loads the Gazebo plugin, and we'll see when we go to leader where the plugin is loaded.
All right, you've got 2 more minutes.
Sure, I'll finish it. Yes.
Right.
And if you see the RVs, sorry, the Zacro related files, inside the Zacro files, we actually include. If you see, this is the main Zacro file. In the main Zacro file, we actually have conditional loading of Gazebo materials and Gazebo plugins. If we are actually only using the simulator, for a real robot, this wouldn't be there. Okay. And after that, we actually load independent files, which are actually chassis, electronics, wheels, sensors, etc. One by one. We create the links inside. So instead of trying to copy paste all the chassis related information, which are actually the same, we create one Zacro file with all the properties inside it. And that properties we actually parameterize and provide that along with the main file that you actually see here. And this Gazebo file has all the Gazebo materials. Normal materials. G3 normal material file contains the materials that are for ROS2, and the plugins and the sensors that we avoided for the real robot contains the wheel parameters, all types of wheel parameters, leader sensors, and the camera related sensors. So this is the organization of this.
All right. Is that all?
Yeah.
All right. Wonderful presentation. Thank you, Venkat. I've got one of my colleagues here. Let me just find out if you've got any questions. Girish,
Yeah,
over
sure.
to you.
Hey, Venkat, how are you? Are you able to hear me?
Hi, Grish. Thank you. You guided me a lot. Assuming I'm talking to the same Girish.
So I'm here for your evaluation along with whatever Chakavarasha is doing there, and
Okay.
good presentation, nice work. So I'm going to ask you 3 questions to evaluate how your project has done and the knowledge that you've gained so far. So
Okay.
while I was seeing your presentation, I found 3 things that I wanted to ask you questions about. And the first thing that I wanted to ask you is, why were you using a fisheye lens for your robot?
Oh, there was no specific there was no specific reason. I just didn't change it. You know, it's like more importantly, I didn't investigate where to change that. I did see your comment in the forum. I should definitely investigate that. It came with the default and it stayed there. I didn't find time or reason to change it.
Okay, that's
I should
understandable.
experiment that. Yeah.
Okay, so my second question is, can you go back to your gazebo simulation?
The simulation as in, yeah, okay.
Yeah, simulation, open gazebo. And can you explain why the laser scanner rays are not on the part of the laser scanner solid, but it's above in the air?
I positioned it there. I gave it, I positioned it a little bit higher. Just when I was making it, I was not able to see it because it was not letting me adjust colors and all. I moved it. I never moved it back. I didn't think it was a big
Okay.
problem.
No, I just wanted to know if you were aware of the simulation.
Oh, yeah.
Because
There is a
in the
property. There is a
simulation,
property I can. Yes. There is a property I
okay.
can change. It will come down if I wanted to.
Okay, because the simulation, as you know, is a digital replica of the real-time situation. So
Yes.
if you're going
It,
to have inaccuracies over here, you will have
yeah.
inaccuracies from the real robot. So
Correct.
I
Yes,
just wanted
because the
to
real
know
robot
if
has
you were
some
aware of
sensor
that.
here. Yeah.
Okay, so can you show me the scanner spinning in the gazebo simulation?
Yes, I need that command. Just One second.
No, you have the controller launch file written there, right? Just start that file, which will start the robot state, the joint state broadcaster, along with the two other controllers to spin the lidar.
I no, it launched it, but I always turn it on by using the command that was there to send the command. Let me just quickly show you.
Okay, I see. Okay, you don't have the
I
command
I
there.
I had to run that command to actually. I didn't think it was. Just let me find that command at the end of this section. There is a
Okay,
command that it spins. No, let me show you. Yes, just
okay.
give me one.
Yeah, that one it is.
Yeah. So if I do that.
No, you can send the command and then you can start. You can then show me it's spinning or not. Can you do a top view so you can
I am
all of us
trying.
can
I'm
see you?
trying. Trust me, I'm trying.
Okay.
I'm trying. I'm trying. Uh,
Okay,
um,
while that happens, I would like to ask you the
yes,
third question without wasting
yes,
much
sure.
time.
Sure.
What did you find to be the advantages and disadvantages parts of using a URDF against a Zacro? What do you think is a easier approach, and what do you think is a better approach, and why is Zacro most preferred than URDF?
I think it comes to mind is that Zacro can do conditional loading of files.
Hmm.
I did not find that property in URDF format. At least maybe I didn't look hard enough. But the first thing that I thought was useful was URDF did not have this kind of functionality where I can do conditional loading. Number one. Number two is in URDF, at least I didn't see the making a block and parameterizing it. I didn't see that in URDF. Okay, or maybe I
Yes.
didn't explore the full spec of URDF, but I didn't see that part where because I started with URDF, right? So I copy pasted chassis again and again and again after doing some
Yes.
research and GitHub. So
Yep.
instead of that, I actually used chassis as a single one when I used to Zacro and parameterized it, which was helpful.
I see. Understood.
Okay,
And
and
a quick question about that. I saw your Zacro files containing inertial values as bigger decimals. Did you not find time to have a macro for that one to
no,
specify
no, I didn't. I
inertials?
didn't find. No, no, I didn't find a macro. I'm sorry. I didn't find time to replace those.
Okay,
When I ran it, it didn't do any harm, and I left it there.
understood. Understood. Okay,
It
so
did
that would
cross my
be
mind that I should empty the entire inertia files when I moved to the real robot, but I didn't find time. It's a matter of time.
understood. No issues. That would be all my questions to you to gauge your understanding. I would I would
Okay,
I would pass
I
this
can
over
move this.
to
No,
Takarasha.
I can move this Girish, but here is you can see it spinning. I am
Okay.
my gazebo is stuck for some
Okay.
reason, but you can see it spinning.
Can you do a top view for in the Argus? Just hold the shift key to move it, and yeah. Okay. Can you zoom in a little bit? Zoom in. Zoom in. Okay, I see. I see. It's spinning a little slow, very slowly, but it is spinning. I see that.
I'm sorry.
Okay.
It's, yeah,
Okay.
that's
Yeah.
it.
That would be all my questions and questions to you. I don't have any other questions, so I'll send it. I will make Takaurasha continue with this meeting.
Okay,
All
thank you.
right. Thank you so much, Girish. Again, Venkat, thank you so much for a wonderful presentation. I was just going to ask one question. Can you explain a little bit why you ended up having to convert back to URDF? For some reason, I think I heard you saying that. Any details you can give
Sorry.
out on?
You're talking about URDF, why I moved to URDF.
What?
No, what did I find more better in Zacro?
No, it was during your presentation that you ended up having to convert back to URDF anyway, even after using Chakra.
Oh yeah, yeah. So oh yeah, yeah. So in the launch files, let me show you where it was. Um, uh, the Zacro file. So basically, what I was doing is I was trying to pass in these parameters, and these parameters I wanted to give a this like this robot description doc to SML. This is in URDF. It was there like that. What I did not explore more and probably did some quick internet search was how do I give these parameters? And looks like I found information where it said first take your Zacro file, convert it into URDF like this,
Okay.
and then give the parameters over here so that it works. Okay. If there is a better way, I did not go looking for it because it worked, so and I left it there.
All right, yeah. I'm happy I got to understand why you had to do it that way. All right, so I think that's it from our side. So, all right, Venkat, I'm gonna let you go now. Then we'll continue on Zoom. All right.
All right, sure.
All right, people. So you can be one of the students who can do a presentation, and then we evaluate you to see how well you have done on your project and on the real robot. So until next time, keep pushing your ROS learning. Thank you so much. Bye bye.